So I'm basically an artist, a writer and a painter, things like that. And the story I'm going to tell you today is about how I came to invent and develop and now commercialize a modular robotic system and get it adopted by about the toughest customer you can think of on the planet for a robot company, and that is the Subatomic Physics Research Institute called CERN in Geneva. So the journey was from an artist to being an engineer. And I should say at this stage that we are an early stage company. We didn't want to put product out onto the market until we were absolutely confident that it was robust and wouldn't fail in the hands of the user. And so I can't brag millions in sales at this stage, but what I can say is that we're innovative. We're up against the big guys in the market, but what we've got is a completely different way of doing engineering to make a robot for a customer. Instead of starting with a blank sheet, designing the thing, delivering it for a task, we've developed a modular engineering system that integrates generic parts and can be customized, working with the customer to produce exactly what they want. So it kind of turns the whole formula of product design, development, and delivery on its head. CERN, for those of you who are not really familiar with the place, is one way to think about it. It's a very big experiment. It's a hadron collider that accelerates particles to high energy levels to do experiments to try and demonstrate whether the physicists have got their ideas right and whether there really is something like, say, the Higgs boson. So the bigger it gets, the smaller the particles they're looking for. And as CERN's actually scheduling an increase in size to look for even smaller particles. And what is really the problem there now is that as they turn the power up, the background radiation is growing, and it's getting tougher and tougher to put engineers into the place to do the engineering work. And that's where we come in. There's a whole lot of different tasks to perform, and it's a really tricky environment. There's even really strong magnetic fields, the strongest on the planet. And our robots can actually survive them because of the way they're manufactured and designed. And it's a great place for us to be with our reconfigurable system. So we have some other customers of a similar type to CERN insofar as that they are all up against the same problem. They've got to get people out of the equation, and these are environments that are really tough for people to work in. So what's required is a robot system that will do the job of a person and handle the hazardous environment or a place that's very hard to reach, or perform a task 24/7, or perform a very repetitive, accurate task, or maybe all of those combined into one. So we're looking at disaster relief, the oil and gas industry, nuclear decommissioning, even agriculture, anywhere where we can make a really big difference. A friend of mine said that it's curious, but inventors often have something in common, and that is that they have to have a time in the wilderness, and it kind of helps get the creative process going. And my wife and I bought a large barn in the south of France in the 90s and started to do it up, to restore it, and that was my time in the wilderness. He also said very helpfully that that the inventors have another characteristic. They often have to let a little bit of chaos into their lives. And looking at the roof that we had to restore, you can see that we got that bit right as well. So the creative process really has to be fueled by a little bit of something extra, a little bit out of the ordinary. What I think I learned from that experience was just being very flexible in my mindset and just persevering no matter what and finding another way to do stuff. So as I said before, an artist, I've been painting and drawing and writing and making things, furniture and ceramics all my life. And my background, my family are all artists or engineers or architects all mixed into one, and I was spat out of the same mold. And I was a dreamy, creative child, and it didn't really improve as I got older. So when I'm out, when the family are out on holiday, I'll be taking photographs of trees, and it's a joke in my family just how many photographs I've got of trees, and this is all for drawing and etching and creative ideas. So when it came to engineering a modular system, I had nothing to fall back on except my experience as an artist. So if we're at the seaside, the family will be swimming and having fun in the water whilst I'm taking photographs of ripples in the sand. And what's going on here is I'm trying to understand the beauty of the ripples and understand maybe what the interplay of forces is beneath the apparent beauty, what actually creates this, what makes it come about. So at one point in my life, I was studying fluid mechanics, and I got very interested in the numbers beneath this and the explanation for what creates beauty. So I will typically be 100, 200 yards behind my family while they're out doing something, taking photographs of things. It might be a palm tree, it might be a detail on a car, and trying to build up a stock of images and ideas. And it's basically a seamless whole, just trying to create as many ideas as possible and try to gel them in my head. This is a semi-abstract painting, a study of mine for a much bigger painting, and it's a landscape with of the seashore with headlands and water and reflections and patterns overlaid over patterns. And what I'm doing here is trying to seek out the sort of emotional impact that these interplaying forces have, a feeling of the big outside world and what feelings that actually provokes in your mind. So my choice of a dog is also influenced by my artistic preoccupations and even engineering ones. This is a sculpture of a Saluki by Giacometti, and a Saluki is a kind of like a greyhound, but for hunting, and it was developed and bred by the Bedouin Arabs. So you see that he's got a deep chest, and he's got long legs, so he's got the lung capacity and the long legs for running fast. He has a tail for counterbalancing his body to absorb energy and damp movement, and he's also got big paws for running on the sand, and he's got a long jaw with lots of teeth in for getting hold of antelope. So he's designed for purpose. So form follows function, and this is my Saluki at the seashore, enjoying a little bit of a breeze, and you see the long jaw and where all the teeth are, the long legs, the big lung capacity. He's designed for purpose. He's a hunting animal, and my wife and I think, have like this kind of dog because we see clarity in the design. So in France, I was building buildings for customers. But I was also making some of my own, with my own hands, trying to reverse engineer the techniques of the vernacular architecture and understand just how buildings were put together. So I would try to use as few tools as possible and use the original materials and reverse engineer the process to better understand it. There's also a kind of minimalism. So this is a pigeonnier, a pigeon tower that I built myself. And it's got a kind of simplicity to it that I find satisfying. But there's also a comic thing going on here, that it's a little bit like the scruffy palm tree on the left, which, if you see, I'm trying to actually extract a little bit of humor from this. The building doesn't have to just be a serious engineering project. And I think that humor is another kind of way of getting to the essence of something. So in this caricature of mine, I was a caricaturist on newspapers for 6 years in the UK. This is a drawing of Samuel Beckett, the writer and playwright. And what I'm doing here is trying to reduce to the essence the Samuel Beckett-ness of Samuel Beckett. So I'm exaggerating and eliminating and stripping away detail to get to the essence. But also the comic part is part of what I think helps me in my design process, even when I'm designing robot systems. Sometimes a little bit of fun can help spur the process on. When I was at university, I had to study literature and dismember other people's literary creations and pick it apart and find out how they worked. And you'll all know that, a bit like little boys taking the wings off flies to see how they work. When you take something apart, it often doesn't work again when you put it back together. And that was the feeling I had about literary criticism, that it was much more fun creating things than actually analyzing and taking things apart. So I try to keep the analytical process really at arm's length when I'm creating, but nevertheless try to keep it there in my mind as I work. And so this is Thomas Aquinas, a writer I got very interested in, and there were 3 words that stuck in my mind that I like to keep there when I'm working: integritas, consonantia, and claritas. And what they mean is, the first one is that there has to be, everything has to be there, and nothing must be superfluous. The second part, consonantia, is that everything must be proportional within a system. And the third part is really hard to define, but it actually means, for me, that moment when you've got a design and it all starts to come together and you start getting more than the sum of its parts. It starts to actually simplify itself and make it really work. These are 3 great principles that I really, really try to hang on to. And when I'm stuck in a corner with a problem, I try to think about them and let them help me. So this is a side elevation of a beetle robot created in the modular system, and it looks a little bit like semi-abstract art. And for me, that's important, because whilst I've had to learn a lot of the stuff that you all will have known a long time ago, tolerancing, materials, all of that, so I've got the kind of classical struggles, I'm also very interested in the look of something, and whether, if it looks beautiful, then maybe something's working right. So whilst this system actually works and the beetle crawls along and it does all the right things, and it's got very few parts to make a lot of complex structures, it also looks a little bit like semi-abstract art. Staying in the analytical mode for a little bit longer, a painter I really admire, Vermeer, has a very structured and organized way of building his paintings. So whilst I'd like maybe another day to talk about how he puts the paint on, what's going on between the artist and his sitter, what's going on in the tapestry, the play with perspective and all of that, fascinating stuff, we could also look at just how he put his painting together in actual formal terms. So I've overlaid some lines on this painting, and you see a square and 3 rectangles in certain proportions. And what's going on here is if you change those proportions, the painting doesn't work quite so well. So what's happening with the painting as it stands is that your eye roves around and keeps moving, but the painting's got a stillness to it. And you could carry on adding lines and getting a little bit more sophisticated. There's more going on than that. But, for instance, here is a relationship between the sitter, the painter, and the light fitting, the chandelier. And it makes sort of semi-abstract art. But it's really important because those relationships are not there by accident. Vermeer really meant them. So, in my own work, I try to, it's a bit like chasing elephants in the fog. Now you see them, now you don't, but it's better not to see them. It means they're probably safely at distance. So the analytical process is a bit like those elephants. I try to keep it at bay, but I try not to forget it. So in my children's books, which I wrote and illustrated, I was trying to practice what I'd studied. So this is a story about white rabbits who have their carrots stolen by some horrible hares. And to get their carrots back, they build a Trojan carrot, present it as a big present to the hares, go into the fortress, leap out, and you all know the story, they get their carrots back. So what's going on in the battle scene is that I want to get that sense of movement and excitement of a battle. And so there's a lot of distortion of perspective, diagonals. There's a massing of solidity and space, a little bit like in the Vermeer. But it's all to express movement and excitement. And where these ideas came from in this particular instance was from Japanese printmaking. So one of the takeaways from that is to see something useful in one domain and use it in another. So this is a photograph of mine of some agapanthus in the south of France. Simple flowers, but what I take from this is the simple patterns that create complexity. And when I'm designing, what I try to do is, if I've got a complex system to design, look for what's simple in that and how a various simple systems overlaid can create that complexity, to try and really take the complexity out of a system. And you'll all be familiar with the Fibonacci series, which is that each number in a sequence is the sum of the two preceding numbers. But what I'm interested in here is in how this tells us something about the way nature creates structures. In this case, a sunflower head. There were lots of sunflowers around me where I lived in south of France, and I used to study them and look at them, and I'd count all the seeds and try to work out whether the textbooks were right. And they kind of seemed to be right, although the seeds often weren't the right number. I think some had dropped out or something. But the point here is thinking about whether knowing about these rather strange sequences in our world help us design something. So this spiral, the Fibonacci spiral, is so fascinating because just like the classical architects who used the golden mean to create what they considered perfection in architecture, like the Parthenon's proportions, so it is that the spiral can be formed out of a succession of squares whose proportion falls into the golden mean proportions of 1.618%. And curiously, when I was developing my modular system, I discovered that this funny number kept coming up when I was working on Solid Edge and I was designing it. This 1.618 kept coming up, and I was really curious. I thought, that's the golden mean, but why is that happening? And I talked to a mathematician, and he said, it's obvious. Your system is scalable in steps, in increments of the golden mean. And then he said, but it had to be. If it hadn't worked that way, you wouldn't have got your system to work. So I think in that instance, what was happening was it was more archaeological than design. It was almost like I was discovering something that pre-existed in the geometries. And that is an interesting thing. It kind of almost corroborates the idea that if you look for ideas that already exist in our world, they can help you in your design process. So there I was, coming back to my little story, this wild ride that I've had over the last few years. I'm down there in the south of France. My wife and I have restored our barn. We can live in it. It doesn't leak anymore. Children are happy. They used to cry in the early days because their house was a tree house. My son came back from school one day with his satchel on his back. We were living upstairs, mum and dad, up a ladder. And he was just standing at the bottom crying. And he said, I don't like this. And we said, well, why? But he said, no one else lives like this. Anyway, we got that part of our life over with. That was the chaos that we brought into our lives. You know, you remember, you've got to have the chaos. Anyway, you take your family along with you in all this. And fortunately, they've all put up with it. They're still talking to me. And these buildings I was making for customers, I was doing all the kind of classic stuff that you all have to do. You listen to your customers' requirements, and you try to do all the trade-offs, the design trade-offs, to get to somewhere you all want to get to. You do, and I was delivering buildings on price, on time, all that stuff. But I was also, because I can't stop myself, pushing the envelope, just seeing how far I dared go. So this building was a really good example of something that could have been simpler, but I wouldn't let it be that way. It was cast in situ in a technique that no one had ever done before. The local artisans complained profusely about this, but in the end, everyone was really happy. And we all learned a lot and moved on, and we all were better at what we did for the next job. So here's a sketchbook of mine from the very earliest glimmerings of what three-dimensional modularity would be. And what I was doing was I think, getting a bit bored with the architecture and thinking about, isn't there something else I could be doing? And the children had construction toys, Meccano, Lego, Connects and stuff, which was great toys, made great toy systems, but there were so many parts. And you needed so many parts to make not that many different toys. And I was thinking, you know, just as an intellectual challenge, is there another way of doing this? Couldn't there be just very few parts that make a fantastic number of really great toys? And I was actually drawing my ideas I learned technical drawing at school. And so with ink and lots of instruments, protractors and things, I was drawing this stuff. And I showed these drawings one day to an engineer at Aerospatiale, building the big jets. And he looked like he'd seen a ghost. And he said, but you're the last person on the planet that's doing that. Haven't you heard of CAD design? CAD. I said, yeah, but I've downloaded some 30-day trials, and they were horrible, and I've given up, and I'm not going to do that. So he invited me to a party, and he threatened to show me this other system called Solid Edge. And I was determined not to get involved. But actually what happened was the midnight came, and unlike in the fairy tales, nothing happened. And I was really relieved. And I thought, great, we can escape. I can carry on the way I know, doing what I know. And then he flips open his laptop, and he shows me this Solid Edge thing. And he lends me the laptop. And within about 24 hours, I was completely won over. Because suddenly all my ideas could come alive in 3D. And this is an early version of the toy system I created with just a few parts. But I was able to build and test them. And I didn't know anyone who was using CAD except for these engineers at Aerospatiale, so it was a total discovery for me that it could do all this stuff. I then started looking at math websites and trying to work out what was the ideal modularity. So I had this powerful tool. I could develop and design stuff, but I wanted to go further. I really wanted to see where could I go. Theoretically, one part did everything. That's what they said on the websites. And I thought, OK, that's the challenge. Let's go for it. Let's see if we can get there. And I had a kind of weird confidence that it would work. And I don't know where that came from. I just thought, this is something that's got to work. And I actually think that what helped me out there was a kind of process of creation where I didn't set any boundaries. If you look at what John Keats, the poet, said about creativity, it's called negative capability. He wrote a letter in 1818. He'd been out socializing in London and was a bit shocked by what he saw, the sort of superficial behavior around him. And he got very interested in what it is that a poet is. And a poet is the kind of person who will look for something and not stop until they've found what they're really searching for. It's a bit like swimming in a rough sea, and you see some rocks, but you swim onto the ones further out. And so that's what it was meant by negative capability. And that was, I think, my process, that I was not setting any boundaries. I was just determined I was going to get it down to one part. So to cut 12 months of intense work through the nights short into a few seconds, I got it down to one part, patented it. It went through, didn't get challenged by anyone. I discovered through my patent agents that no one had ever thought down these avenues. And I think probably what it was is they never ever spent quite so many nights endlessly trying to find this thing. They'd never bothered. So I get it down to a single part. I patent it. Fantastic. I've got something that's potentially quite valuable, but I don't want to give up my architectural business. So I'm hedging my bets here. I keep going with the architecture. I develop the system to a cool toy and an educational system, and I think, well, maybe license it. I don't have to set up a business and create a product and go through all of that. Just license the thing. So that nearly worked. I got to a point on a Friday afternoon where I was negotiating with Hasbro, and it kind of nearly happened. But the main thing about this story is it didn't happen. I didn't get showered in gold. I was left holding my patent and my designs and a big problem burning in the middle of my life, which was what to do with this thing. And so I thought, well, why not set up a company and look at a completely different set of markets from education and toys, which is low margin, high volume. And in these images, you see a brightly colored dragster car that the system can create, and then you see a rather duller looking but highly reconfigurable and much tougher looking robot. And the point here is that I started doing some research. I got some investors. I set up a company, went back to the UK, left France, packed down my business, and gave all my best work to my main competitor, as it turns out. And I researched the markets that I thought needed help the most. And these were the ones where there were people in dangerous, tricky environments, difficult tasks, all those things I was talking to you earlier about at CERN. But what I hadn't realized, and this is kind of the law of unintended consequences coming to play in all of this, remembering that chaos coming into your life, there was all this to do. And as you'll all know, a young technology company with a stack of very challenging technology to develop, the two don't meet very comfortably because you need finance and you need expertise and you need time to survive. So here you see a picture of one of our robots being lowered into a sewer. And you think back to the toys, what a long way that is from a child's playroom. So I'm going to look at one or two of the design leaps that had to be made to actually get this system from the child's playroom into sewers, nuclear power stations, offshore oil rigs, sandstorms, Colombian forests, you name it. One of them was the connectivity of the platform. How to connect all those modules so that some guy, let's say, on an oil rig in the dark can connect them and make them all work, and he doesn't have to understand the system. And how would the system then be very robust and yet make it affordable so that maybe some of our customers who don't have big budgets can still have it? So there are all these challenges. And I looked at connector companies, and I thought, wow, they're very sophisticated. They've got years of experience behind them. They know how all those little fiddly bits of metal and plastic fit together. There's tolerancing issues. We can't compete with those guys. So what is it that we know that they don't? I was thinking, well, I've got this system of geometries in my head, and I'm familiar now with Solid Edge of making structures and so on, and experimenting and really getting somewhere very quickly. And what emerged was a coaxial power and data and physical connector without tools, made of plastic, but if you think back to my architectural work, also using new techniques. So I hunted down a means of metallizing plastics and bonding the metal to the substrate, and therefore making lightweight, low-cost connectors that can handle very high levels of current and also lots of data in a format that we can produce in series, in large numbers. And so the connectivity was therefore solved, but by going back to my roots and keeping the system simple. And so the cross-section you see, the wireframe drawing, looks very complex, but all the geometries within it are very simple. And it's just the combination of all of them that brings about the complexity, but it's a very simple system to actually use. Another challenge that we had was that we were talking to all these customers. I'd set up this company. We were talking to customers about what we could do for them. They completely got the idea that we could reconfigure the platform, make it smaller, make it bigger, put lots of tools and sensors and artificial intelligence on it. That part was great. But the bit that they didn't get was, yeah, fine, but how are you going to get your robot up our oil rig? How are you going to get it into the jungle? How are you going to get it across the sand? What about if there are metal steps? All of that kind of stuff. So mobility was raising its head. Like wheels, tracks don't do the job. What will work? So I started thinking, maybe there's another way of doing this, and maybe I could learn something from the world of arthropods. And this big picture of a cockroach shows you that one thing we didn't want to do was try and build a cockroach in mechanical forms. That's really complicated. So I thought that biomimetic engineering there's two ways of doing it. One is slavishly try and make a cockroach. The other one is, what is it about the cockroach that works in an unstructured, unpredictable environment that you could actually adapt in simple engineering terms? So I started thinking about a big hero of mine, Gaudi, the architect, and how he designed the pinnacles of the Sagrada Familia Cathedral in Barcelona. And he used the parametric design input principle of hanging strings with little weights, and that gave him all the different structures and their relative proportions and the curves to get to where he needed to get to. It was very hard otherwise before computing for him to work that out. I thought, well, okay, why not then try something similar with mobility and make lots of little legs? And so on this robot you see legs. These are a small version of the bigger version. But essentially all I was doing was trying to put legged gait onto revolute actuation. And the difficult part of this was to get the legs to behave themselves correctly all the time without any high-level intelligence, like the cockroach. The legs are all passive adaptive systems, so that no matter what the terrain, they tend to do the right thing because of the compliance, the way they're actually structured and proportioned, and the way that they can pivot. The process was really quite quick in that what we did was we would do some field testing of the robot and try it on very difficult obstacles and actually tune the system to get to a point where the geometries and the materials gave us the desired result. And you see here a robot with its foot on a step, a slippery step. It puts a little foot out, but the other feet bend inwards. And over big obstacles, the feet always tend to find a grip and help the robot up, and it'll even run through bramble bushes and things like that. So there are lots of characteristics of these legs, if you like, and feet that are very desirable, but very simply produced with a straightforward motor. Another part of the design process was to, in this lower sequence, was to work out, if I want a low center of gravity, string the robot really low, what happens when I bottom out? And going back to those principles of keep it simple and look for a way of getting more, like Claritas, more out of your system than the sum of its parts, I thought of just stringing a track under the robot's belly, run by the existing actuation devices, and make a problem become an advantage. So when the robot bottoms out on the railway track in the lower sequence, what you see is the robot's actually getting secondary traction. In fact, it goes more quickly as it gets onto the railway track, not more slowly. Another part of the development process, that dizzying stack of challenges that we had as a young company, was how could we make this system really robust and really affordable and lightweight and man-portable and all of those things, all contradictory requirements. So I got very into this thinking of monolithic construction, where you combine different materials in the manufacturing process, and you get a really great result. You get something with few parts that won't fall apart because there are not many parts, and it's easy to maintain and repair, and it's easy to use, and does a great job. So on the left, you see a jack plug, which is part of our communication system, and it was 21 parts at the outset, and it was a horrible thing to assemble, and it went wrong, and it was just dreadful. It's now one part or two parts, depending on how we manufacture it. And what's really, really nice about this is that it works brilliantly. It can take any amount of punishment. It's very cheap to manufacture. And there's nothing to rattle loose and fall apart. And there's nothing to assemble. So on the success of that, and now our company, I have some technicians finally in the equation helping me out, looking at how can we do more with less in the system. And so the cube you see at the middle, which is how we build our robots, it's like going back to kindergarten. You build your robots with little cubes, and you can build up bigger and smaller robots around the cubes. What we're doing now is running the power and data looms through the structures and just trying to get it so that there's not much to assemble and there's not much to go wrong, and it's lightweight and cheap to produce. Another preoccupation of mine, going back to that Saluki discussion about the beauty, because he's got that lovely tail, he moves, the tail absorbs the energy, it balances him, it dampens his movement, he's very flexible, was that we didn't have the luxury of building robots in steel. And thank heavens we didn't, because when CERN got our robot, they did a quick experiment in one part of the Hadron Collider with a steel box, which got chewed up like tagliatelle by the 4 Tesla magnetic field. And then they put our robot in, and it was fine. And the reason was that we don't build the robot out of metal. We use composite materials and non-magnetic metallization processes. But also, the robot's very, very robust. So when I went back to CERN, they said, we love your robot because it's just so robust. It looks cheap and plasticky, but it's so robust. I said, why do you think it's so robust? And they said, because the energy is absorbed through the whole structure. There's nothing that's single, there's no single failure point in the structure. So to extrapolate all of that, I started getting more and more interested in putting things like tails on the back of the robots. So this little robot, which is designed to be thrown, can have a longer tail or a shorter tail. And what the tail is doing is it's damping movement and helping the robot move over a difficult terrain and absorbing energy. And we can have a flexible tail and we can ballast it. So that's coming back to thinking about how animals achieve things, living creatures, and then seeing, can we breathe a little bit of that really useful stuff into our robots? There's another element as well, and that is have a bit of fun, because when we first made that robot called the iBoyd, people just screamed with laughter. They said that's such a funny-looking thing, but they also understood what it was designed to do. So this brings me on to the brand, because, of course, it's all very well to design a technology, but it's got to be understood in the marketplace in terms of there's got to be an integrity between the brand and how people understand its use and how they're going to use it. So I think this wasn't very complicated for me. I went straight back to where the whole thing had come from, which was Euclidean geometries, and thought, well, why don't we just keep it really simple? It's a whole lot of cylinders, cubes, simple geometries, don't get elaborate, and never drape the robot with abstract forms. And so that is a simple design principle that I carry through the whole way. And one thing about the way this technology works is that you can read in the technology how it gets used. And so that follows through into the brand. So where we are now in the evolution of our company is that we've got to a point where we've got all these customers. They've all got similar but different problems. They need to get people out of the loop and use robots in place of people. And we've realized slowly, because all these things have come not in any intended sequence. If you think back to my construction toys and then into the design evolutions of the robot system, one thing I can say absolutely truthfully is I didn't see where this was all going. Where we've got to is a platform technology, which you might liken to, say, like an iPhone, which has apps on it. And the point here is that a platform technology is an enabler so that you are helping two different groups. You've got a user group for whom the platform's great because they get what they want cost-effectively, time-effectively, it de-risks, there's lots of cool apps. And for the supplier side, what's really great for them is they get to sell a product to people, customers they'd never normally have got to. They don't have to build a robot. They can just use the platform. They can supply LiDAR scanners, arms, abrasive jet cutters, cameras, hyperspectral imaging sensors, and artificial intelligence to our customers. So that is really where we've got to in terms of the evolution of our company, a platform technology. And what's really exciting here today is that we've got to a point where the technology is quite mature, it's ready to go, we've got customers, and it's certainly got me out of southwest France, because I'm now traveling around the world into lots of different walks of life and finding out about so many different fascinating workplaces because of the robots. So you'll find me one week in a chicken farm, next week in the Hadron Collider, next week messing around with some rescue people, trying to see what do you do when a building's collapsed. That's the kind of areas that we are focused on, and that's what's getting me running around, trying to understand the customer and trying to give them the solution set that really meets their requirements. So it's turning into not so much a hardware proposition as a solution provision proposition as a company. So if I've got some takeaways from this, one thing before I give you any of the formal takeaways is I don't actually recommend what I've been doing. It's not prescriptive, but if you really, really want to risk messing up your life completely, be very flexible in your journey. Go and restore a barn with a 3-year-old child in tow and just see what happens. The other thing I'd say is be really confident you're going to win out, in spite of the fact that you've got everything stacked against you, and it's never been done before, and it's just theoretical, and in theory it's impossible. And the third takeaway I'd say is just use anything, and don't let anyone put you in a box and tell you it has to be done this way. Just look around life and just see what you can bring to the party to make it get really exciting. Even if it's humor, that might help you in your design. Thank you.